You guys personally, what you would like to, if I manage to finish this one earlier tomorrow, and we have like an hour or something, would you like to hear something like medicine, machine learning in medicine, microscopy, or autonomous driving, or maybe a deep learning lecture? Or maybe the unsupervised, maybe a PCA.
PCA.
PCA, okay. Igor, do you have any preferences?
Not really. Well, all is new for me, so.
Always good, okay.
Always good, yeah.
Okay, okay. Do you feel overwhelmed?
No, right now, no, but actually I'm thinking about practical implementation of all the stuff. So just from economic perspective, this really can be used like for FMCG sector, but for large holdings with not lots of clients, actually I don't see like good implementation, but I will find. I think I will find. I would like to prepare and train my own model using the lecture code maybe.
Yeah, I hope that you guys can reuse the lecture codes, whatever we had programmed in the Jupyters. So you can, if you come across the same problems, you can reuse the same code. That would be perfect. So I don't know exactly the economic, maybe from economic perspective, was the great example of the application of such models. I mean, I think it would be fair to say that linear regression is something that is fairly used everywhere, all over the place. I mean, all sorts of forecasting. I'm pretty sure you can find it there. I mean, we will look at the time series, which is the closest you can get to economics with machine learning. So maybe we can find some nice example there. But from my personal experience, my real personal experience, I have given talks at an energy company. So there is Energy Estonia, Eesti Energy. That's how they call it. And what I have talked there was that basically you can use these models to model, for example, the battery recharge times, right? So you have the supply and demand of energy. Like everybody, except for Lena, everybody wakes up at like 8 or 9 and they go and take shower, right? So that's where you need a lot of hot water in your tap. And this means that you need to warm it up, and that means that there is a lot of demand on energy. So actually predicting this demand is what very good. What machine learning methods seem to be very good at, and these methods like time series, they have been. Oh, Kenneth, you have a great background. Is that your hobby, or to climb the stuff?
It's my business.
Oh, it's your business. Oh, pretty cool.
So I forgot to turn it off. Later on, I have to do something as if I was at my business. I was just seeing what it looks like. If it looks convincing that I'm there, but it doesn't.
Oh, yeah, kind of, some parts of it detach at some point, but yeah.
I'll find a better background. I will turn that off. But
you yourself, you do not really like professional climber.
It's what I do. I get paid to do climbing.
Oh,
and to run the business.
Okay.
It's different versions of what it means to be a professional climber, I guess.
Okay. No, that's definitely in my vocabulary. That's definitely being a professional climber. All right. Let's get back to business then. Not that kind of business, but still. So we just calculated the residual, right? So this is minus 0.8 is the residual between what we have predicted, the black dot, and the green dot, which is the real y value of the point, right? So we can, so that's why the residual word here is what used in residual sum of squares. So when somebody is saying, can you calculate the residual, it means can you calculate the difference between the predicted value and the real value. So whatever somebody's using a fancy word residual, you know what it means, okay? So taking minus 0.8 to the power 2 leaves us with 0.64. And then we do it for the other points. For example, for point number 2, Igor, what would be the predicted value for the point number 2? Can you calculate? Can you tell me what's the predicted value?
3.4. Yeah.
So what did you do? I'm not as good in quick math as you are. So please tell me, what did you do?
0.6 multiply by 2, then add 2.2.
Yeah, right. So 3.4, right? 3.4, as you were saying. But the real value is 4. The predicted value is 3.4. All right. So if anybody has any questions by now, they should be more or less clear. We could do it for the point number 3. That would be basically 4 predicted value, and the real value is 5, so it's 1. And then we can calculate it till the end for all the points. These are the values of residuals that we have. And the sum of these residuals, which is residual sum of squares, is 2.4. So Olena, what is 2.4? How can you interpret this 2.4? So if I'm asking you what is, how well your model does, you can say 2.4, right? It doesn't really say, like you can't really compare it to anything, but it is just a way to estimate how well your model performs. You can say, well, my model has RSS of 2.4. This is the way how my model performs. This is the error of my model, 2.4. Does this make sense? Lena, does this make sense? You're like, okay, it's a late night at Toronto. It's like, I don't know even that this is the nightmarish hour to me personally. You're a very strong person. You can survive this sleepless nights. I'm not sure why you torturing yourself so much. But I appreciate that you actually on the call. So what we do, or we can do, we can calculate these RSS values for different types of lines. So let's say, for example, Igor was saying at the end of the previous part, he was saying that I tried the number of trees to be 9, the max depth of the tree 9, right? And I get better performance. Here we can say the same thing. For example, Igor comes along and he's saying, hey guys, what if you try, instead of this W1 that we had here, 0.6, right? So here we had 0.6. He's saying, hey guys, what if you try 0.6, 0.7, 0.8, 0.9? Which one would have the lowest RSS? Which one would have the lowest RSS? Simon, what do you think? Would 0.9 W1 equal to 0.9 would result in better RSS?
No.
Why do you think so? Why wouldn't it result in a better RSS? What's the reason for you saying that?
I maybe didn't understand the question.
So imagine
we have the vector and we have x.
Okay, so let me just re-explain that part. All right. So this line here, this dashed line here, has an equation of 2.2 plus 0.6 times x, right? So 0.6 is the slope of the line, right? You remember Kenneth told us, I remember, he said that this is a slope. 2.2 is an intercept. So this is this point here, 2.2. What am I saying is we have calculated RSS for this line, for this equation here, and it turned out to be 2.4, all right? Now what am I asking is, Igor, by the way, it's not me asking, it's Igor came along and he's like, you know, guys, what if you try different slope values? So instead of 0.6, what if you try 0.7, 0.8, 0.9? So each one of these would result in its own line, in a different line with a different slope. And now I'm asking, do you think that any of these lines have high chances of having lower RSS than what we have calculated right now? So why do you think so?
RSS should be higher because we will have higher slope, means we will have much higher error on 0.4 and 0.5, for example.
Yeah, in fact, you can say that the model that we have right now, that this line is the perfect line because we calculated that this is a perfect line. We have actually calculated this intercept and 0.6 slope as in we solved the linear regression problem. We solved it, and this is the best you can get analytically by calculating these values analytically. But well, it still doesn't stop us from trying. So we can say, well, this is 0.6. The RSS of 0.6 is 2.4. What if we try 0.7? Well, the RSS increases to 2.95. What if we still, what if there is still anything good afterwards? And we tried the 0.8. RSS gets really bad. And then it's just awful. It's just awful, right? So the higher we go in terms of slope, the worse the RSS becomes, okay? It's just to illustrate that you can try different models and you can compare them based on this RSS value, all right? You can compare different models based on their RSS. Any questions here? Does this make sense to you guys? Igor? You look like you have a question. You're like, nah, that I'm not buying this. Okay. You're muted, by the way, but I'm reading lips. I can read lips of my students. I actually can read looks and I can read lips. You're still muted. I'm reading your lips and I'm reading your looks. Like Olena is right now thinking, like, why am I doing this right now? Actually, read minds of people. Anyway. So these are the loss functions. So we're getting back to the loss functions, and we can just put them all together and we can call them error. So every one of them is a type of error. For BSE is a binary cross entropy, is an error for binary classification problems. MSE and RSS are errors that are used to assess regression models, okay? But they're still errors. So what happens is that we can add a sum of squared model weights to the total error, and we can call it L2 regularization, right? So we can add something that looks like this, that has a W and lambda and I and N, and I'll tell you what these two mean. But basically this WI in terms of linear regression is W1. This is the only weight that we have in our model, which is called slope, which is W1. So for the linear regression problem, this basically results in error plus lambda times W1 squared, okay? This is called a L2 regularization. And you probably know it because I saw that Alexander had these slides. And we're just going to look into more details how exactly these things can be used in practice. So if we just write it up, this would be lambda times and the sum of this W squared. Okay. L1 regularization, on the other hand, what's the difference with L2 regularization?
What do you mean, what's the difference?
So this one is L2 regularization. How L1 regularization is different from L2 regularization?
I don't know.
Okay, so it's very simple. It's just a sum of absolute values of weights, right? So here we have a square, and here we don't have a square. That's all there is. Okay, so it's just sum of weights, absolute values of weights. Have you guys seen that, Igor? Did Alexander say something like this? Oh, okay, that's new.
I think he said, yeah, but to be honest, I maybe didn't get it.
the concept. Okay.
The concept.
Anyway, so this is L2 regularization, and this is L1 regularization. And now we will check out how exactly this thing works on linear regression case, okay? Yeah, by the way, just if you just write it out, then some people get scared by the sum symbol. So if you just drop the symbol, it will be lambda times and then the sum of the weights, right? In terms of linear regression, Olena, how many W's do we have in the linear regression that we just saw?
5?
How many?
5? I don't know.
Oh, no. I mean just one model, not 5 models, but just one model. Let's say W1 equals to 0.6. I'm just trying to get you say just one W. It's just one W in case of linear regression. So this is type of questions that are obvious, and then you start thinking there has to be some kind of caveat in the question, but there is no caveat, so it's very simple. So linear regression has just one W1. I mean, in that case that I showed you, it has just one W1. It can be applied to more features, and then you would have more W's. For example, in a previous lecture, we saw how you can use a linear regression on a problem with 2 features, and then you would have 2 W's, all right?
Are you about to talk about the difference between L2 and L1, I guess?
Yeah, absolutely. That's what the lecture is all about mostly. The first part of it anyway. So apart from minimizing, so normally when you train a linear regression model using scikit-learn, for example, package that we saw, what it does, it minimizes this RSS function, right? So it tries to make sure that its RSS is the lowest possible. But when we add the regularization terms, either L1 or L2, it basically adds additional constraints. It adds additional problems for the model. So it now has to take care also of being of having low weights. So this slope should be as low as possible, because it also tries to minimize the entire sum of error plus the regularization term. And you will see how does it work. This is for somebody who is a math gifted person. Simone, I'm looking at you. You were, before the lecture, Simone was complaining, saying that there is no integral in your lecture slides. I don't buy the lecture slides without an integral, especially double integral or triple integral. So this is something that maybe make you a bit happier. So why the hell? So what's the difference, and why do we call L1 and L2 regularization? Because there is such a thing called L2 and L1 norm, right? So L2 norm is when you take basically a square sum of things. So you take things into square, and then you take a sum of them, but you take a square root of this sum, right? So you have a square all over the place. Here's the square, here's the square. So the L2 regularization is a squared L2 norm. So you put this into square, and you get rid of this 1/2, and you just end up having a sum of squared stuff, right? And here I show it. I show it in an example, right? So I just take this stuff, I take it into square. These two guys get a mutually exclusive, and then you just get the sum of squared weights. Here we are. So L2 regularization is a squared L2 norm. And that's why it's called L2, because you just take L2 norm and you square it. Okay, so L1 norm is just the sum of weights, absolute values of weights. And L1 regularization is just L1 norm of vector W. So you take some of these stuff, and this is your L1 regularization. This is just for those people who were wondering why L1 and L2 norm, L1 and L2 regularization has to do with L1 and L2 norm. This is exactly what it has to do with L1 and L2 norm. It's just a small math discourse, but it's not very important for the rest of the lecture. So if you have any questions about that one, go ahead and shoot. Otherwise, we can proceed. Okay. Go going back to the example that we had, right? So we had this 5 dots. Now let's imagine that we have only, so we basically say, what if we use just 2 dots for training and 3 dots for validation? So we kind of lose this other half, right? So we just forget about it for a second, for some time. So we just concentrate on this training data. And we calculate all the same stuff. Just to estimate what's the equation of the line that goes through these 2 points, we calculate these things. So what's the, Igor, what's the average of X value here?
1.5, yeah.
What's the average of Y?
3.
Good. And then we calculate the other things. I won't torture you too much with that. Sum is 0.5, sum is 1. What's the W1? Who remembers? How can you, out of these 2 guys, what was the W1? Which one you divide by which?
1 divided by 0.5.
Gotcha. This is great. 1 divided by 0. This is 1. This is 0.5. So this one is 2. So you got.
What's the denominator again? I was trying to remember the word.
Sure. So you basically take the covariance, which is this one, and you divide by the variance of X. Right. This is covariance between X and Y, and you divide it by variance of X.
Thank you.
All right. So this is a slope. All right, so this is 2. Now, all right, so what is W0? Simeon, since I kind of referenced you like a math gifted person here, can you give me a W0 now? No pressure, by the way.
W0?
Yeah.
Ah, it's this the intercept, excuse me.
Yeah, the intercept, yeah, the intercept.
Yeah. It looks like 0.
It looks like 0. Why does it look like 0? Because you take 2, you multiply by 1.5, and you have 3 equals W0 plus 3, which makes it 0, right? So this one looks like 0. Okay, so this is our line. This is what the line equation that goes through these 2 points. Perfect. And this is the perfect linear regression for these 2 points. Now what happens is that we need to calculate, well, the error obviously of this line with respect to training data is 0, obviously. The error is 0. Since I'm kind of calculating it here, but you guys know that it's 0, right? So it should be 0. But I'm still calculating just to make sure. So it's 0. But now you remember, okay, this is model number 1, okay? This is model number 1. Let's imagine, just imagine, okay? Just imagine that we have a model number 2. And I told you that we will use a slope of 1.5 for this model, okay? Let's calculate the RSS for this model, for this 1.5 times X model. So we do all the same stuff, all the same calculations as we have done for the RSS of this model, and we get 1.25. So if we would be forced to decide between these 2 models, let's say these are 2 models like we just had in the Kaggle competition, one and the other model, we would choose the one that has the lowest error, which is the model number 1, right? But let's see what happens if we introduce L2 regularization here in the picture. So now L2 regularization is in the picture, which means that when we calculate the error, we also calculate the weight. We add a weight squared to this error. By the way, this lambda factor, we haven't talked about lambda factor before, but this is a strength of the regularization. For now, we just assume that lambda is equal to 1. In other circumstances, we need to find the best lambda via cross-validation algorithm, okay? Any questions here? I got a little bit fast in this place. I was a bit faster. So if you have any questions, then let me know. Yeah, so what we do is we recalculate the error now with L2 regularization, right? Olena, I have a question to you. Can you help me out with that? So what's the error of the first model in this case? What was the RSS of this model?
0.
Now we add L2 regularization to this error. What is this L2 regularization term for this model, given that lambda equals to 1? This
2.
is a $100 question now.
I know 2.
So what is L2 regularization? Remember?
Squared. Okay.
Sum of squared weights, right? How many weights do we have, Igor? How many weights do we have in model number 1?
Weights? Well,
Weights.
1.
1. We have just one weight, which is
2.
2. So what would be the L2 regularization term for the first model?
4. Yeah.
4. Amazing. 4, of course. So the error for it, the entire error, Simeon, would be 4, because we add 0 plus 4. That's the entire error. Yeah, exactly. So this is what happens. We take RSS plus the regularization term. And in the first case, the RSS was equal to 0. And the sum of squared weights was 4, right? In the model 2 case, it was 1.25 RSS. And so the first model would be 4. But what about the second model? What about 1.5 squared? What's the 1.5 squared?
So plus the same weight. It's a different value, but it's the same number of weights. So you'd have 5.25. Correct?
Okay, wait. So let's just let's get back to this. How many weights do we have in the model number 2?
1.
1, which is 1.5, right?
Oh, but I'm going to square that.
So what is the square of 1.5? People, can you help us?
2.25.
2.25. So the sum is 3.5, right?
Yes.
So yeah, so okay, here I actually show it, right? So this is the W1, right? We square it and we sum them up. So it's 4 against 3.5. Do you see the trick? Ladies and gentlemen, do you see what happened?
Yeah.
Oleg, what happened?
Happened that no matter that what is
Don't
called,
worry, no pressure, just try to formulate it. It's, you know it.
I forgot the generic form for this errors. RSS, yes. Besides that, RSS was smaller, even 0 for model 1, yeah, than model 2. Then, let's say, integrated error, vice versa, yeah. It's less for model 2, yeah, than for model 1.
All right, so
it's opposite to RSS, yeah, relation.
Somehow it has overweighted the RSS. It has overwritten the RSS. Yeah. So RSS was not as deterministic for this difference as the difference in terms of weight squared. Now my question is, so I mean, obviously we would prefer the model 2 now, right? So the second model has lower error, and so we do not have intercept as part of the these L2 penalty, because intercept is not considered to be a weight of the model. So this is something you guys should remember. So intercept is not considered to be a part of the model that you can tune, because usually the intercept is the average of the entire of your data of the dependent variable, right? So it's just whatever you have in the training data, your dependent variable, the average of that would be your intercept normally, right? So you don't really take it, you don't really consider it to be a part of the trainable model. So that's why you don't include it also into L2 penalty. You only include the W1, starting from W1. Yeah, so we have errors calculated on the training data, but we also had validation set, right? We also have validation set. So we now can calculate these errors for the validation set. To be honest, at this point, I really got tired of drawing arrows. This is the number and that number, and then again, this number. So what I decided is just to switch the points of view, and I decided to use the vector notation, right? So now we have vector notation. So we have it for model number 1. Can somebody help me? Can you help me with that? So the first operation is inside here, right? So we multiply 2 by this x. What would be the resulting vector?
So 2 by, so 6 and 8 and 10.
6, 8, and 10. What would be the result of the next operation?
1 and -2 and -5, I guess.
So it's -1, -4, and -5, right?
Yes.
And then we square it. What's the square version?
So 1, 16, 25.
1, 16, 25, exactly. And then we add the weight squared. What would be the weight squared? Oh, by the way, sorry, you need to sum it up. Sorry, you need to sum it up. So what's the sum of this?
20, 30.
32.
32. Yay, 42. Yeah, right? 42. And then add the squared weight, which is, Olena, which is, you were the responsible. You are unmuted. Can you say?
4.
4. So what's the result? Quick.
46.
Yay, great. Awesome. 46. Gotcha. Now we do similar stuff with the other model. So we compute the error, and it's 12.75. Okay. So for the validation set, it turned out that the second model is performing much better. The takeaway from here is that the L2 regularization forces models to prefer smaller weights, right? It actually prefers models with smaller weights. What you should think about, the way how you should think about this is slope. You can think about slope as a matter of dependence between the independent variable and dependent variable. So the way how your model depends on this feature. Sometimes, and most of the time in machine learning, we are trying to not really depend heavily on none of the features, because basically it could be a noisy feature. So there might be a noise, and then everything will be screwed. It also, somehow when we prefer one feature over all the other features, it might be that it's just that there were so many features in the data set that one of the features, it was correlating with the dependent variable just by pure chance. So if you imagine, for example, human genome, how many bases, do you know how many DNA bases there are in the human genome?
A lot of.
Approximately, what do you think approximately is the number of bases in the human genome? Okay, thousands.
More.
Oh,
Millions.
billions, I think.
Millions. Maybe billions. No? Too many?
I feel like billions is good.
Billions is the good. Actually, it's 3.6 billion. So 3.6 billion positions in the DNA. in the entire so basically in the deployed version, so in both strengths. And you can imagine the problem of classifying a person's phenotype. Basically what you see, for example, having a dark hair or the light hair, or having this height or this height. So you basically have a data set that has 3.6 billion positions in features. So 3.6 billion features. And you have, let's say, 100 people, right, that you're trying to classify. So sometimes by random chance, you can come up with there might be a feature that is just by random chance is super nicely explaining the dependent variable, but it's actually just a noise. Okay, and when you take another 100 people in this, another 100 people, this feature will not say a thing about their color of their eyes, for example. So that's why usually in machine learning, we consider high dependence on features as a bad trait. We are trying to get rid of that trait by using, for example, regularization. So by using regularization, we are trying to make models less dependable on any specific feature. We are trying to make them more general.
I have a question. So yeah, so it's a bit, I mean, so L2 regularization, because all it is just a by definition, it equates error with the size of weights. Is this used only in machine learning, or is L2 regularization exist outside of machine learning in any instance?
I think it's a very so if you would agree with me that machine learning is basically stats on steroids, then we can say that this is stats and machine learning.
Okay, so it's a mathematical way to get people to stop overfitting stuff, kind of.
Yeah.
Okay.
I haven't heard of other use cases of L2 regularization. That's the truth. I honestly haven't come across other applications. Any other questions about this? Lena, do you have a
Why
question?
we use L2, not L1? How we decide?
This is a very good question, and when I'm going to compare L1 and L2, you will see the difference. There is a very important difference between these two, and there is a very specific scenario under which you can use L1, not L2, and the other way around. But just give me a second. I will come to this example. Do you guys have other questions before we move on to a little bit more elaborate example of regularizations?
And also,
Sorry,
yeah,
go ahead.
Please go on.
Just so to follow up on it, so if in fact you have a model and one weight, there is in fact actually super high correlation, and it actually does an excellent job, and it's not random, this regularization will punish that model even though that model is a good model. So that, like, how do you
Exactly.
stop?
Exactly. So what Kenneth is saying, and as far as I interpret, is that what if it's a genuine correlation? What if it's true that this feature predicts the outcome? The thing is, in that case, L2 regularization will actually perform worse. The assumption here is that in unseen case, in the unseen data, so you have your data and you're saying that is a true correlation, but in unseen data, this correlation will not be as good as in your training data. So there might be something else. And this something else will be maybe the domain shift. Have you heard of domain shift? This is when you were using, for example, one company to track your customer behavior. And then you suddenly started using the other company to track your customer behavior. And there is some difference in the way how these companies operate and the way how these companies actually track the customer behavior. And then you suddenly started getting slightly different data from the other company. And now if you were really solely relying on one feature from the previous company, now the other company may not have that feature, or this feature may not be as perfectly correlating with your outcome as it was for the previous company, then it would make sense. But otherwise, it's a very important comment that actually it may hurt your performance. So using L2 regularization is necessary when you see overfitting. When you test your model on unseen data and you see that there is a huge gap between the training model performance and the test model performance. In that case, it makes sense to use L2 regularization. If you see there is no overfitting, then you will hurt your performance. So there is no, everything comes with a price, and this is the price.
Mm-hmm. But also here, one more, let's say, dimensionality, this is a lambda value, yeah? Because you can also play with the lambda.
Absolutely, absolutely. Lambda is deterministic, and we will see how it affects the performance of the L2 regularization. It's very important to find the proper lambda. Exactly, and it takes effort, and it's takes care. Any other questions? Simeon, go ahead, shoot.
No, everything clear, thank you.
Igor, you have been silent for some time. You're fine? Everything's okay?
Yeah, everything is okay.
Cool.
Clear is for now.
Okay. Okay. So yeah. So linear regression with L2 regularization, will have smaller slope W1 than the one without L2 regularization. So the regularization can be made stronger or weaker depending on the value of lambda, right? So we were using so far lambda equal to 1. So we assume that this is the standard lambda and we use the lambda equal to 1. But in fact, you can use many other lambdas. So this was a lambda equal to 1 and this was a model number 2. If you would use other lambda, for example, lambda equal to 0, what would be the model that would result from the lambda equal to 0? Igor, since you said there are no questions, so what would be the model? What would be the result of lambda equal to 0?
So x is equal to, so the dependent variable is equals to independent variables, like that. Or no, even so we don't have any weights in a model.
So we wouldn't have any regularization, right? There would be no regularization.
No, yeah.
So we would only have this error part. So right, so we would just have error part, which is model number 1. We didn't use regularization for model number 1, and we ended up having 2 times x. You were right. We can also use other lambdas, for example, lambda 3, lambda 4, lambda equal to 5, lambda equal to 6, and then something really big like lambda equal to 1,000. And then when lambda equal to 1,000, no slope will be allowed. So you wouldn't be able to stand up upright because the penalty for slope would be such high that even a smallest slope would be penalized so heavily that you wouldn't be able to raise your model from the ground. So the lambda is super large, then the model is forces its slope to 0. Okay, that's definitely not lambda that you should be using. It's just to kind of, for interest's sake, what happens, right? Just to see what happens if you make it really, really large. If you make it really, really small, then you will just have a regular linear regression. If you have it somewhere in between, you will have L2 regularization with some certain lambda. Okay. Any questions about it? This rainbow chart?
Well, why to stop? Why stop?
Why to stop? So that's why to stop, because at some point you basically end up with a flat line.
No, when to stop.
When to stop. And that's yeah, go ahead, Oleg.
Can it be less than 0? For example, 0.5?
Absolutely. It could be less than 0. No, it could be less than 1. Sorry. It could be less than 1 between 0 and 1. Yes, it could be 0.5, could be 0.25, and so on and so forth. When to stop? In fact, this is what the cross-validation algorithm is meant for. this helps to know where to stop. You take several lambdas, and then you train a cross-validation, and then you check which one produces the smallest error. And that's pretty much the way how to find the best lambda in the case. And the second homework exercise has a cross-validation algorithm for the searching for the lambda. So you can be searching for a lambda. This is one of the homework exercises. Any questions? Any other questions?
Can it be less than 0? For example, 0.5.
0.5 is more than 0, Oleg. I regret to break this bad news to you, but
less than okay, yeah. So
0.5, yes, absolutely, it can be 0.5. In fact, you will find out that this is the close to optimal lambda is less than 1.
Okay.
To be honest.
Okay.
So 1 is very strong regularization actually. Usually people use something between 0 and 1, something closer to 0 in fact. No, answering your question, no, it cannot be less than 0. It cannot be -5 or something like this, because that's what people, I think it didn't really, it wasn't useful. So it would mean that you would subtract from their weights. I don't know, maybe that's the next breakthrough in machine learning, but I don't, I haven't seen people doing it. No, it's no, without jokes. It could be something that it may be pretty cool. I don't know.
And conceptually, what is lambda? Like what's, when you're thinking?
So the interpretation of lambda is the strength of the regularization. So how strong is the regularization, the coefficient of the regularization?
You know, I understand that, but so when you say the strength, you mean how much we think the data set we have is vulnerable to noise? Is it, I mean, like if we have a noisier set, then we're thinking higher lambda. If we think we actually have a very good or simple set, is it higher lambda if we have lots and lots of weights in our model, lower lambda, less weights? Like what's, like conceptually, what's the thought process?
Got it. I got the question. So what the question is, what's the intuition? When we should choose the higher lambda and when should we choose the lower lambda? So lower lambda, well, basically if your model, like a neural network, has a lot of weights, then you know that summing those weights up squared is going to be a huge number. So you better choose something small for lambda, something like 0.0001, for example. If you have a model that contains just one weight, like this linear model, then choosing lambda equal to 1 is completely fine. So it depends on the model more than on your data. You should think in terms of how many weights and how large the weights are in the model. Yeah, that's definitely a very good question. So think about the model, think about the how many weights do you have, and then try to balance this out. Because if you have too large penalty, then you wouldn't see the actual error. So that is a problem. Looks like a lot of fun, but the basically it doesn't. The linear regression trained on one variable will not be powerful enough to overfit. So there is no real use of L2 regularization on linear regression on one variable. Doesn't really make much sense. But let's add a small twist here. So so far we have been using a one dependent variable, which is y, one independent variable, which is x, and this was pretty linear, right? It was very linear. How can we make it a bit less linear, a bit more flexible? Any ideas? How can we, out of here, produce something that would be nonlinear? Any wild expectation, something that you
x squared. Yeah.
How do you call that? Take and add x squared and x cubic and x to the power of 4. How do you call this?
Polynomial.
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 So that would be a polynomial. So we take x, we don't have any other data, but we have x. So we square x, we take a cubic power of x, and we take a fourth power of x. And this is how we generate additional data. So we are trying to generate data out of nowhere, right? So we take a square, cubic, and fourth power, and then if you apply a linear regression on these data now, this is going to be called polynomial regression, right? This is now called polynomial regression. You see how easy is that? You just had one single feature, and now you have 4 features and polynomial regression. And you will see that it's much more flexible. In fact, the equation for this polynomial regression now looks like this. It has 1, 2, 3, 4 weights. Now there are 4 weights instead of just 1 weight. Well, plus intercept, of course. So this is why intercept. Let's see how the linear regression that is trained on this data will look like on this original graph. By the way, I'm just showing x to the power 1 because I can't really show you 4-dimensional space. I can only show you 2-dimensional space. So I have to choose one x. So I decided to choose the original x. Okay. So if we train the polynomial, so this polynomial regression here, polynomial model, we trained the linear regression on this data with error function RSS without any regularization. Here's the line that, okay, sorry. This is the error. This will result in this line. So if you train a linear regression, which is this, on this data, you will get this line. Trust me or not, this is the line that you will get. Moreover, you will have this equation of the line. This would be the equation of the line. So this is an intercept. 5 is an intercept. And then you have W1 equals to 8.8, W2 equals to 7.8, W3 equals to 2.3, 2.3, yes, and then 0.2 last weight 0, W4. Any questions here? Okay, makes sense? Have you seen that? Polynomial regression? Okay. That's all good. Do you guys, okay, so just let me go back here. Does this look like a perfect recipe for disaster?
Yes, it looks like it's overfit.
Yeah, it looks like it's awfully overfitting, right? How do you know? How do you know? If you look at the trend, right, and you look at the extreme values, like in before the first point and after the last point, you can see that it definitely doing something wrong. It's definitely not doing something nice, right? Plus, it wraps up the data perfectly, which should ring a bell. Should ring a bell. There's something going on here. Yeah. So what if we add the regularization term now? So to the error function, which is a normal error function that we used to have, we just add a sum of weight squared, weight squared with lambda. And lambda can be different, as we figured out. And Oleg was pushing this lambda less than 0. I cannot really promise less than 0, but I can promise less than 1. So let's see how different, linear regression with L2 regularization with different strength of lambda will look like for this specific case, right? So this is the lambda with, this is the regularization of 0.1. This is how linear regression with lambda of 0.1 will look like. You can see that it has already gone better. It has already gone much better because it didn't have this wild turn before the first point, but it still has this kind of weird stuff happening here and there. Plus, another thing that you should should pay attention to is the size, the value of the weights. So you remember that this one is 8.8, 7.8, 2.3, 0.2, and so on. So when we apply linear, when we apply L2 regularization, the weights get smaller. When we increase the strengths, so we increase the lambda factor, the weights get even smaller. So and the line gets even smoother without this wild turns. It gets smoother, and then it gets even smoother and smoother. Right. So this is the final line with lambda equal to 1. And this is the final equation. So if you compare the equation with lambda equal to 1 to the original equation that was without lambda, you can see the difference, right? So every weight has decreased. Also decreased the intercept, but this is just a kind of side effect. It wasn't modeled explicitly. Yeah, do you guys have questions about this? You can see that the model has, as we call it, higher variance, so it's more flexible. More flexible than the linear model, than the line, right? But it's still not as flexible as the black line, right? Not as flexible as the black line. So what we are basically usually saying is that it has some part of variance. It does have model some variance, but it doesn't model it so so strongly so that it would overfit. Okay. Any questions here? I think Oleg, you were saying something.
No questions.
No questions. Okay. Anybody? Questions?
But in this formula, the last x power 4 looks not necessary in the formula because it is too small.
It's like in machine learning community, it's not yet too small.
Mm-hmm.
Too small is like 0.00001, something like that. That is too small. But this is kind of moderately okay. Any other questions? Olena, are you still conscious, present here? How are you?
Does it make any sense to use lambda 0.55 or like?
Yeah, makes sense. Makes sense to use any continuous value. Unless, I mean, as soon as it produces best results, you're absolutely welcome to use any value. And it just boils down to the fact, how do you find these values? That's the only question. Igor, do you have a question about this one?
No, it's black magic.
Black magic. I don't know what the hell is happening here. No, seriously, do you understand how did we end up having this line?
Yep.
Gotcha. Nice. There is an elephant in the room. Oh, sorry, there's somebody who was saying something.
Kenneth, yeah, I was just, I mean, it's a little slightly off topic, but so like using the squared and cubed and whatever values of x, this is a way to try to model strengths of relationships without having high weights. Is this kind of what ends up happening?
Strength of relationship without weights. I think it's an attempt to make the model more flexible. So it's an attempt to make it less linear. So no, I don't think it's actually models any kinds of real. You're actually right. I actually let me say it bluntly. I don't know.
Taking x and then you cube it. Now that value is higher, but then so like it's a way to model that strength. But then you say, okay, but don't take it too seriously by then increasing lambda. These kind of things are working against each other in some way.
Yeah, that's true. That's true. We are. I guess from the geometrical perspective here, these polynomial degrees of polynomial, they add flexibility to the linear regression, right? So we add a bit of square of this parabola curve to the decision boundary. We add a little bit of the cubic curve. We add a little bit of the curve to this power 4. So basically, I think I can interpret this from the geometrical point of view is that we try to model. So we try to make a model that consists of multiple polynomial curves. Okay. At the same time, we are trying to contain it. We are trying to keep it safe, to try to somehow restrain it.
We are trying to add waves to the straight line.
Yeah, basically we are trying to add some waviness of the line, right? So but at the same time we are using L2 regularization just to somehow keep it sane, keep it stable. Yeah. So this is the approach. And by the way, Simeon said, I guess, that this is a small value, and this is basically saying that we don't really need so much of the x to the power 4 curve in the decision boundary, right? So basically, we don't need that kind of twist in the model, or not that much of that twist in the model. So elephant in the room. Olena was saying she had a question. She was like, well, actually, both Olena and Kenneth, they were asking a question about L1 regularization, right? So Olena was asking, when should you use L1 comparing to L2? And Kenneth was asking about L1 in general. So the elephant in the room is L1 regularization, right? So here is L1 regularization. On the first sight, it looks like another type of curve. It doesn't really, it doesn't really matter. Just another type of twist. But there is an important caveat comparing to L2 regularization. They are very similar. So the only thing that is different is this square here and absence of square here. But there is an important difference. If you look at the equation of the model that is produced with L1 regularization, you will see this difference straight away. What's the difference, ladies and gentlemen? What's the difference?
Zeros.
Zeros. So what does it? How can you interpret that, Olena? What do you think? How can you interpret that?
I have no idea. I don't know.
Anything that comes to your mind. Zeros are nice, looking like, some kind of sweet bread. You can eat it, whatever crazy things that come to your mind, say it. No? Okay. Anybody else?
It means that the x itself does not make any effect on the prediction, and x square also.
Yeah, it forces some weights to be close to zero, like this. It just simply considers them to be useless, right? It says you don't need these features. I can do much better with the twice features you had in the beginning. So so L1 regularization is used as a feature selection. It's not, we don't really, in machine learning, often use L1 regularization as a regularization per se. I mean, training the model and that kind of stuff. But rather, usually people run L1 regularization on their data set as a pre-processing step, as a feature selection step. So you try to model whatever you're trying to model, and then you end up having less features than you had in the beginning. Okay? That's the kind of, that's the purpose of L1 regularization, is to do a feature selection.
But it's interesting though that it's set to zero, the two features that L2 regularization gave the highest weights to.
Yeah. I don't have a good comment in here, but that's true. That's true. So you can see that it has mostly used the cubic curve to describe the relationship. Yeah, I don't know why it set to zero, not the last two, but the first two
had the highest weight after L2 regularization, right?
Yeah. I don't know why did it. It's just that's the internal implementations of the L1 regularization. I actually have. So wait a second. I'll get to the to some links that I wanted to share about this one. So the question that Lena actually asked is, when should I apply L1 comparing to L2 regularization? So L2 regularization is used to reduce overfitting. So when you train a model, machine learning model, for example, neural network model, then you use L2 regularization to fight overfitting. You use L1 regularization to do feature selection most often. So that's the main difference. L2 is to reduce overfitting. L1 is to do a feature selection. Okay. This is just to summarize it.
Is there a preferred order of doing that? Do you do L2 with all of your features first and kind of have a look and then apply L1 to the model that L2 discovered? Or do you do feature selection and then apply L2?
So you do, you first do feature selection usually, and then you apply any other model on feature selected data. That's usually the sequence.
The opposite of the order we just did it.
Yeah.
Actually,
any other questions, Igor?
Actually, with this New York City taxi challenge, we could add like polynomial expressions.
Yeah,
functions.
yeah, absolutely, absolutely. I love the way you think. I think it's a very nice idea. I haven't thought about this. And you know why I haven't thought about this is because this was my lecture number 4. And text example was in the lecture number 1. It's for this course that I'm giving lecture number 1 and then lecture number 4. That's why they're so close, and you can actually think about the application of L1 and L2 regularization on this taxi data set. So yeah, absolutely. Go ahead. This is one of the ideas for the last exercise. Absolutely.
But actually, is there any kind of an algorithm that helps data scientists to approach the
preprocessing?
Huh?
Preprocessing, the feature selection kind of stuff.
Preprocessing, maybe like everyone starts from kind of linear regression, then polynomial, then regularization, then decision trees or something like that. Is there any algorithmic process, or this is all like purely how to say, творческий?
Creative process. So so what Igor is asking is these things like preprocessing and feature selection and then training models, it seems like a fairly standardizable piece of functionality, right? Something that you can actually create a function and then just run it for any data set. So would it work for any data set? So you just give it the data set, you say, I want to optimize fair amount, I want to predict fair amount, and the rest of the thing is done by the algorithm. So such algorithm exists. It's called AutoML. You know, as the name suggests, you give it an algorithm, you give it a data set, and you're saying, I'm interested in that feature, and then the rest of the thing is done by the algorithm itself. Being honest with you, I don't think that machine learning people use it. Because I think that it is the creative process, as you were suggesting. I think many data sets, so many approaches are very data set specific, and they are very domain specific. For example, you wouldn't do the same preprocessing as you, for example, for the data, for the taxi data set, as I would do for my imaging data sets. All right. So if I have a car here, and if this car would, so the car has what is it? 4 cameras, right? So there are 4 cameras on the board, and we take pictures of the environment. And then we need to find pedestrians, street lines, and cross marks, and traffic lights, and all that kind of stuff. So the preprocessing that I would do for this car would be very different from the preprocessing that is done for the taxi driving data set. And then if you take something completely different, like sound analysis. So these things are still something that you should know by yourself. So we will be talking about regularization method that's called augmentation, which is basically very image oriented. But in principle, people normally don't really trust these AutoML methods. So they usually they prefer to use something built by themselves. But they exist. But let me say it this way.
So can I make a hypothesis or a hypothetical of working? So let's say I have the taxi data, and I want to do more. And it turns out that actually I can get all this sensor data from every taxi, like air pressure of tires and whatever. And I think to myself, you know what, maybe this will help the model. And I throw all this into, suddenly I have like all kinds of data that might not be important. So this is like now where I would do L1 regularization to say, okay, like all this junk I threw in that I probably think it's not useful, let's drop out some features. And so I would do much more of the feature dropping out kind of work first when I have a sense that the features might be useless, or if I'm just kind of playing around with, you know, finding some surprising connection that, oh, actually, you know,
that makes sense, right?
Makes
There's
sense.
some interesting connection here.
Yeah.
Absolutely.
So is that sort of the, you're talking about the art of it? Is that the type of thing you're talking about?
Yeah.
Like
yeah. Well, another art of it is, I mean, this is one thing. Another thing is, consider this taxi example when we talked about hover sign distance, right? This is a feature engineering piece that these kind of algorithm like AutoML wouldn't perform. So you would actually, there is a way to combine these longitudinal coordinates and latitudinal coordinates in a way that you get just one feature out of 4, which is very useful. And this is type of thing that that you as a person who is an engineer in a company that performs this kind of operations, you would know because this is your domain. You're an expert in this domain. But somebody random like me, for example, who is working in bioinformatics, I would never know that. And if I would be making this algorithm that should supposed to work on all the possible all the possible data sets, I wouldn't know that trick. So this kind of trick stuff is what makes it an art to some extent, creative process to some extent. Knowing your domain and for example, if you know for a face recognition problem, it's very important to find the distance between eyes and distance between eyes and the mouse. This is very detrimental for a face. So each one of your faces have slightly different the distances between eyes and mouse and nose and that kind of thing. So if you calculate all these distances, I can fairly quickly tell your face is one out of, basically distinguish between your faces. Well, if I would be this kind of machine learning algorithm, I would say, I don't care. I would just do my regular whatever I do, and then I'll hope that my random forest will do the job, which may not be the case.
Well,
okay.
Another question, if you let me.
Sure, go ahead.
In this task for New York taxi fare prediction, we could take hour of a trip, not day, but just hour, like 9 a.m., 9 p.m., 12 o'clock or something like that, and use these hours as a feature, just to how to say, just to take into account daily seasonality.
As dummy variable, you mean?
Yeah, as dummy variable. This is time series problem or no, as for now?
Yeah, it is some time series problem. It is time series problem, meaning that you have actually a timestamp for every. So yeah, you can transform it into time series problem. You can transform it into time series.
And vice versa. I can transform it into.
Exactly. Yeah, you can transform time series problem into static machine learning problem. Absolutely. If you extract a feature of, let's say, what's my months of, let's say if you have a revenue of the company per month, then you can say, okay, I'll just create a feature months, and I'll treat it as a static machine learning problem. I have a friend of mine who actually, sorry, Kenneth, you were saying?
Kind of category.
Yeah, exactly. So I have a friend of mine. She wrote a paper about analyzing time series with static and dynamic machine learning methods. So if you have heard about something called LSTM, this is a deep neural network that is used to model sequences. LSTM is very good at modeling sequences. It has been one of the best in modeling sounds. So there has to be some dependency on your input from the previous input, right? And LSTMs have been used to model time series. And I was hoping maybe we can get there, I'm not sure. And she compared the LSTM with this static approach, as exactly as Igor is saying, it's just extracting some categorical variables and then treating it as a static machine learning problem and basically using some random forest or decision tree algorithms on top of that. So yeah, and she I think she compared it, and she said that the combination of two is actually what performs best in all the most possible circumstances.
Mhm.
And about the combination, we will be talking about this during the second half of the course. We will start with ensembles. This is going to be about this ensembles. Okay.
And in terms of the Python, so as far as I get, for L1 and L2, we should have in the Python several functions that will help.
Absolutely, and this is what we're going to do tomorrow. I think there is not enough time today. I have, so I shared the regularization notebook with you in Slack, but we're not going to do it today because there are like 7 minutes left. I don't think there is, it makes sense to go for the code. But tomorrow we are going to do the L1 and L2 regularization. Let me finish the lecture, just a couple of slides left, and then we can have a bit more QA.
Okay.
So just to finalize it, just to polish it up. So every machine learning algorithm, almost every machine learning algorithm can be used with L1 or L2 regularization. Okay, you can add it as an additional feature. And you call that machine learning model with L1 or L2 regularization. Easy peasy, lemon squeezy, that's how you call it. But it's not as simple in all the cases. Sometimes, for example, when you're dealing with a specific type of machine learning algorithm called linear regression, as we were dealing with you today, when you add linear, so this is a linear regression. When you add L1 regularization to linear regression, you end up having something called lasso regression. And when you add L2 regularization to linear regression, you end up having something called ridge regression. So this is called lasso regression, and this is called ridge regression, okay? So normally when you use any machine learning algorithm and you use L1 or L2 regularization, you say, well, that's a machine learning algorithm with L1 or L2 regularization. But if it's a linear regression and you use L1 on top of it, then it's lasso. So it's a very scary term. For myself, I was confused for so many years before I discovered that lasso is nothing more than just simple linear regression plus L1 regularization term. Easy peasy, lemon squeezy. There is nothing to be worried about. The same about ridge, okay? It's a linear regression plus L2. Lasso is an acronym. It stands for a least absolute shrinkage and selection operator. That's what the acronym LASSO stands for. And you can always, you can see that the shrinkage, selection, it's called like feature selection. Basically, it sounds like feature selection. This is a feature selection method, basically. You kind of drop a lasso on the features that you like, okay? Ridge regression has another name. It's called Tikhanov regularization, okay? It's proposed by Andrei Tikhanov, who has been working at Moscow State University. So this is called Tikhanov regularization. Arguably, L2 regularization is one of the most popular regularization techniques in the entire machine learning community. So when you hear somebody saying that I use regularization, usually it means that they use L2 regularization. Okay, not L1, not something else. There are other methods for regularization that we will go through during this lecture tomorrow. But when people say I use regularization, usually it means that they use L2 regularization. Okay. This is what we have discussed. So I took some of these parts from videos, and I really suggest you to look through these videos. You know what? Today I will make a post. I'll make 2 posts actually. One about links that I used for the previous lecture, to make the previous lecture, and another one with these links that I recommend you to check out. They will be all on Slack. Please go and join Slack if you haven't joined Slack. Let's keep the conversation going in Slack. I will be posting all these links because it will be a nightmare for you to, check out the PDF and then try to find the same video by the name of the video, not by the link. So I'll be basically copying the links into the Slack so you can click and just watch it straight away. I just wanted to specifically emphasize this video about lasso regularization, since I didn't lasso regression, by the way. You don't say lasso regularization, you say lasso regression. Since lasso regression has a very nice property of this feature selection. And this video explains why the hell it actually ends up having some of the coefficients reduced to 0. It actually has a very nice explanation why the hell some coefficients end up being 0. I think it's pretty nice, pretty interesting. And the last question before I guess we would stop is, do you guys know how the L2 or L1 regularization is called when you go for deep learning? So when there is a neural network and you use L2 or L1 regularization, how do you call that?
Backpropaganda.
No, backpropagation is the algorithm that is used to train the deep neural networks, which is I absolutely happy that you know the name, but it's not about regularization.
The same,
so
like
what is?
Yeah, I know the name of Harry Potter. Yeah, I can name this Harry Potter magic.
Yeah.
Propaganda is the same for me.
Back propaganda. That's actually the most fascinating way I've heard people saying version of backpropagation algorithm. Thank you for enriching my vocabulary. Olena, do you know how do you call L1 or L2 for deep learning? Kenneth, do you know how do you call L1 or L2 for deep learning?
No, I'm guessing I've already been taught it, but I don't know what it is.
You forgot about it. Okay.
Well, no,
So
I mean, I knew about lasso and ridge, but I never put it together.
Okay. Okay.
With L1, so I figure it's
okay. Gotcha. So it's called weight decay. So when you hear somebody saying weight decay, it's actually basically L2 regularization under the hood. Okay. So and now you know everything about L2 regularization. So when somebody is saying weight decay, you're like, I nailed it. I just know what the hell is that. Okay. This is all for today. Thank you very much for being here today. And I'm hoping we can finish that part tomorrow. And we have Kahoot for tomorrow. We have Kahoot. We have code. We will do a lot of more programming, and we will test L1 and L2 in the example data. And we will also train deep learning models tomorrow in Keras, as you have done previously in the other course. Okay. Yeah, and I'm happy to get more questions. If you have any questions, and I'm just absolutely the happiest man alive if you ask me questions. If there are no questions, I'll be not as happy person, but I'll still be okay.
Let me make you happy. Regarding decision tree, yeah, in decision tree, we don't have weighting coefficients, yeah. How do we, let's say, make this penalty for decision tree?
Yeah, so basically, before recent time, I was thinking that L2 and L1 regularization cannot be used for decision tree altogether because of the same reasons as you mentioned, Oleg, because there are no weights. So what can you apply the L1 or L2 regularization to? But then I figured that you definitely can. It's just, I guess I haven't figured out exactly what they use to regularize, but I still have this kind of vague feeling that it's the number of leaves that they use to regularize. So this is another way to describe. So basically, what you apply the L2 or L1 regularization is on the complexity of the model. So you're trying to reduce the complexity of the model. So number of splits is one way to describe the complexity of the model. And I'm thinking that this is what they, but you know what, I don't know exactly. So I might take it as my homework exercise is just to figure out what exactly they use regularization on, because I don't know myself, to be honest, specifically. But that's a very good question. I have asked this question myself. I did very sketchy Googling and I couldn't find it. And I would love to know, because I know that, for example, XGBoost is a adaptive gradient boosting on trees that use a regularization. So there must be a way to use regularization, but I just don't know exactly what they use regularization on. Any other questions? Then let's call it a day. You have been working hard. It was 4 hours straight, so you must be tired. I guess it's a nice idea to go and have some rest and come back here tomorrow at 9 o'clock, and we will be talking about regularization in other machine learning methods. We'll have a lot of code to go through, and we will have a Kahoot. So yeah, if you have no questions, then see you tomorrow.
See you tomorrow. Thank you. Bye.
Thanks.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye.